Hello everyone, and welcome to another instalment in our lunchtime webinar series in association with AURPO. Today's is on shielding X-ray rooms, the basics and a CT example. As always, I'll just quickly run through the ground rules before we start. So firstly, with the questions, you can always ask questions at any point throughout this talk through the Q&A box. It should be, I think, top right of your screen, a little question mark inside a speech bubble. So click on that, ask questions as we go along. What you can also do is like any of the questions that you would also like answering, and at the end, time permitting, we'll answer as many as possible, starting with the most liked first. Also, please register your attendance for CPD points. The info is on the screen now, and it'll also be cut and pasted into the chat, so you can note it down then as well during the talk. And if you've not read it already, please take a look at our latest magazine issue. There's some really interesting articles in there. The link is on the screen. And then final plug, if you're not already a member, please join us. All of the benefits that you could be getting are listed here on the slide. So without further ado, I'll hand over to Professor Pete Cole, who is SRP past president and current president of AURPO, to introduce our speakers for today. Over to you, Pete.
Thanks, Sarah. I'm delighted to say that we've got two speakers today to do a double act, so to speak. And it's both of these gentlemen, I have to say, are heroes of mine in the radiation protection world. And it's my delight to introduce them. Professor David Sutton has a PhD in medical physics and until recently was head of medical physics at Ninewads Hospital in Dundee, having worked in radiation protection and diagnostic radiology physics for over 30 years. He is now retired from the NHS and holds an honorary chair from the University of Dundee. David is currently the Secretary of ICRP Committee number 3, Chair of ICRP Task Group 113, and a member of ICRP Task Group 108. He has been a member of the editorial board of the British Journal of Radiology and is a past chair of the British Institute of Radiology Radiation Protection Committee, the IPEM Special Interest Group in Diagnostic Radiology, and the SRP Medical Sector Committee. David has served as an expert in radiation protection for the IAEA. He is presently a member of the Committee on Medical Aspects of Radiation in the Environment. He is also the current chair of board of RPA 2000 and has edited, authored and contributed to several textbooks, monographs and other publications, all in the field of diagnostic radiology physics and radiation protection. He contributed to and edited both editions of the BIR publication, Radiation Shielding for Diagnostic Radiology. Dr. Colin Martin worked as a hospital-based medical physicist in radiation protection in Aberdeen and Glasgow for over 30 years. He is now retired from the NHS, but is an honorary senior lecturer at the University of Glasgow. Colin is Vice Chair of ICR Committee number 3, Protection in Medicine, chairs ICRP Task Groups 108 and 116, and is a member of Task Group 117. He has been a member of various IAEA committees and carried out missions for the IAEA as a radiation protection expert in Europe, Africa, and the Middle East. He is a member of the UK Committee on Medical Aspects of Radiation in the Environment, the editorial board of the Journal of Radiation Protection and Radiation Protection Dosimetry. He's been a member of several UK radiation protection committees and working parties. His research interests include radiation protection, diagnostic radiology, radiation dosimetry, and non-ionizing physics. He's an honorary fellow of SRP and was awarded the Healthcare Gold Medal by IPEM in 2018. He has co-authored or edited several textbooks and monographs on radiation protection, written over 300 articles, including 170 papers in peer-reviewed scientific journals, and contributed to both editions of the BIR publication, Radiation Shielding for Diagnostic Radiology. So without further ado, I will hand over to David and Colin, and I think, David, you're speaking first, is that right?
Yes, I am, thank you. Okay, well, thanks very much, Pete. Thanks for that very fulsome and kind introduction. And hello, everybody. Just to give you an overview of what Colin and I are going to talk about, I'm going to spend a few minutes giving you a whistle-stop tour of the basic principles underpinning radiation shielding in diagnostic radiology, and then Colin's going to spend some time giving you an in-depth view of how to shield CT rooms, including some background as to how he got the data or how we got the data in the first place. So, okay, so why are we interested in designing shielding? Well, the basic purpose really is to minimize dose to members of the public and staff in a way that fulfills our legal requirements in terms of dose limits, whilst keeping things proportional. In other words, not just putting 3 millimeters of lead or whatever everywhere. It's a bit of an art and a bit of a science. There are actually several ways to do X-ray room shielding, one of which is the NCRP 147 method from the USA, which is outlined here. Another is the German DIN method, where tabulated leg thicknesses based on the types of room and workloads in minutes are used to determine the amount of shielding. And there's the UK method, or the BIR method, which calculates shielding based on doses and related workloads. What we're going to talk about, unsurprisingly, as we're involved in writing it, is the BIR book, Radiation Shielding for Diagnostic Radiology, which is available free of charge, this is a plug, from the BIR bookshop, PDF only and electronic version. But it's really important to notice that whichever approach you follow, do not just use the methodologies as recipes. So if you use the NCRP calculators, for example, you'll get a solution for the US that's based on US practices, US dose limits and dose constraints, not a UK solution, and it certainly will not be proportional. So we really recommend that whatever you do, you understand the methodology and do not use it as a recipe. Also, before we start talking about basic principles, it's probably worth pointing out that at the planning stage, given the expense of purchasing X-ray equipment and also of building rooms, that undue emphasis shouldn't really be placed on cost. We recommend using a specialist shielding supplier where at all possible. And surprisingly, the RPA, architect, building contractor, and all sorts of other people should discuss the work prior to commencement. That sounds like a no-brainer, but quite often doesn't happen. Before you even think about what you're going to do, you need to know what the room's going to be used for, what does the room look like, has someone actually built it already and asking you to comment on it, and what equipment you're putting in. And most importantly, is there a project team? And if not, how are you going to put it together? And if so, how are you going to communicate with it? And just to repeat this, shielding design isn't something to be done in isolation. As well as the RPA's input, which is mandatory, as we all know, according to IRR 17, lots of other people will need to be involved. And again, things should not be done in a vacuum, should not be done in solitude. You need to consult all of the people who are listed here. And of course, you're going to get copies of the slides, so I'm not going to really go through them. Okay, so on to basic principles. Here's an outline of what I'm going to talk about. Dose limits and constraints, a wee discussion on dose, something about occupancy, something about radiation sources and barrier calculations and transmission, discuss how we approach the problem of primary and scattered radiation before summarising and handing over to Colin. Okay, so here are the three environments that we're interested in: the X-ray room, the X-ray control room, and the surrounding area, which may contain patients, other workers, and so on. Visitors, members of the public. And the dose limits we've got are annual dose limit for workers is 20 millisieverts. Annual dose limit to members of the public is 1 millisievert. And we're not really interested in doses in the X-ray room. We're interested in ensuring that anybody outside of the X-ray room gets a radiation dose that's proportionate. And the approach that we recommend is an ALARP solution to ensure that people don't get all the dose from one source. And rather than try and allow for the fact that radiation workers may be in the control room and have a different dose, design dose limit for the control room, we could treat the control room and the surrounds the same. And we suggest that the maximum, that's the design dose, maximum dose allowable from the X-ray facility or the X-ray unit in that area is 300 microsieverts a year, which is 3/10 of the public dose limit. That is our constraint. 3/10 of the public dose limit. A possible exception to this is PET, where you may have to do something for people who are workers in control areas, but luckily we're not talking about PET today. Okay, so just to move on. So dose limits are expressed in terms of effective dose, and I'm sure everyone's seen this ICRP slide that shows how operational quantities, protection quantities, and physical quantities are related. Effective dose is, of course, a protection quantity, as are organ absorbed dose and organ equivalent dose. But the practical measurements that we can use, we can measure air kerma, we can measure ambient and other doses, and perhaps we can measure absorbed dose. We cannot measure effective dose. Effective dose is a sex-averaged risk metric, and it depends on the X-ray spectrum, both the primary spectrum and the scattered radiation spectrum, the beam geometry, and the posture of the person, actually phantom involved. So it's impossible to measure, difficult to calculate, and it's a tool for risk control and legislation. It's not really something that we can use in practice. So what doses can we measure in practice? Well, we can measure personal dose equivalent, we can measure ambient dose equivalent, or we can physically, with an ionization chamber or other similar device, measure air kerma. So these are our possibilities. In diagnostic radiology, the most usual thing to measure is air kerma. So when we started thinking about shielding, we wondered what the relationship was between kerma, HP10, E, H*10, etc. And using data from ICRP publication 116, we were able, oh sorry, 116, we were able, using the coefficients in there, to identify how kerma at X-ray energies, so Bremsstrahlung spectrum up to about 120 kV, related to E, HP10, and H*10. And we identified that in all cases, 70, 85, 100, 125 and below, K is always greater than E. So kerma is always greater than E. As you'd expect, HP10 is always greater than E, and H*10 is always greater than E. So the take-home message is effective dose is always less than air kerma at diagnostic X-ray energies. But measured dose equivalent is always bigger than air kerma, which is an important thing to measure when you're doing assessments of shielding, because as I'm about to tell you, shielding is based on the assumption that air kerma equals always less than effective dose, so greater than effective dose. But if you assess shielding using a film badge, then you're going to identify that the doses are apparently higher than you think. But essentially, it's safe to use an air kerma constraint of 0.3 milligrams per year as a surrogate for 300 microsieverts per year. This is because air kerma is greater than E by between 5 and 60%. So it's a conservative approach. Using air kerma is a conservative approach. So that's the first thing. We can just measure the air kerma out of an X-ray set, work out how much of that air kerma is incident on a barrier, and use that to determine the thickness required. It will give us a conservative estimate of shielding. But if we're going to use constraints, we actually have to think what we're talking about. And the constraint of 300 micrograms per year is a dose to an individual. So that's who the dose limit applies to. It applies to an individual, not to an area. So our design limit has to take into account the fact that people are not going to be in an area for 100% of the time. So we need to weight the dose constraint by an occupancy factor and divide 300 microgray by T, which is our occupancy factor. Now, ideally, you should evaluate the occupancy factor according to the situation that you find yourself in, but that's quite difficult. So in the publication, we make some recommendations that you can use if you're not able to accurately determine what the real occupancy factor is going to be. And here's the list. So for example, control rooms, nursing stations, offices and adjacent buildings, we suggest a factor of 100%. Areas that are partially occupied, like staff rooms or reporting rooms, suggest a factor of 20 to 50%. And for occasional occupancy, for example, toilets, unattended car parks, corridors and stairways, suggest a factor between 5 and 12.5%. Again, you need to decide what the exact factor is going to be. There are some issues with occupancy factors. They're subjective. You might find a problem where there's a high occupancy area behind a low occupancy area. It can lead to potentially high dose rates in low occupancy areas. I'm not going to go into that, but that might have an impact if we consider the 7.5 microsievert per hour instantaneous dose rate regulation. If someone in the future decides to reallocate a low occupancy room for another purpose and make it high occupancy, then you really will have to reevaluate the shielding, and that can be quite difficult because it's just practicalities people forget. And it's easy to underestimate occupancy in low occupancy areas, which might lead to bigger doses than you expect. However, occupancy is really something that we do need to include. It's not proportionate to just say everywhere is 100% occupied. And as we go on to think about the shielding that we were going to do, we need to consider what our sources of radiation are. So there are two types, really: primary radiation and secondary radiation. Primary radiation is transmitted radiation incident on the patient or directly on the barrier. Secondary radiation is that radiation that's scattered using the Compton, by means of the Compton effect. And we have leakage because all X-ray sets leak. So let's talk about primary radiation first. Primary radiation is orders of magnitude bigger than secondary radiation, but it's only of interest in plain film radiography, because for all other types of radiology, so interventional, where we use fluoroscopy equipment, CT, bone densitometry, the primary radiation is all absorbed by the detector or the detector in its housing. So we only need to consider primary radiation in radiography. Secondary radiation, however, is of interest in every modality: radiography, fluoroscopy, CT, mammography, etc. Because scattered radiation is everywhere. Scattered radiation is the primary cause of radiation to members of staff, also, as you know. Scatter depends on the volume irradiated, the primary spectrum, the field size, angle of measurement. It's quite complex. We also have to consider, as I said, leakage. Luckily, leakage is constrained by an IEC standard, which I've written down here. 1 milligray must be less than 1 milligray per hour at 1 meter at the maximum kV that the tube can cope at its maximum continuous MA. Most radiography is carried out at less than 100 kV, so leakage is immediately reduced by a factor of 70 anyway, because it's not carried out at 150 kV. And in actual fact, leakage is between 100 to 1,000 times less than scatter. So we can't effectively ignore it. So we do. So what we're concerned with in terms of the primary radiation are primary radiation for radiography, secondary scatter for all modalities, and something that I haven't quite mentioned yet, but Colin will cover, is tertiary scatter, where scatter from the patient is reflected off the walls onto the people that you're trying to protect, off the walls of the ceiling. So. Right, so a simple explanation of what we're trying to do. If we have a source here, then an air kerma at distance d1, the kerma at d2 is the air kerma times d1 squared over d2 squared without a barrier. If we put a barrier there, then the transmission, the measured kerma is the transmission times the same equation. So that's the transmission of the barrier B. And that is the crux of the problem. It's to put a barrier in the way that gets the transmission to, that gets the kerma to the value that you want, i.e. meets the dose constraint. And this explains shielding in a single equation. The transmission through the barrier must be less than the weighted dose constraint divided by the annual air kerma at the point. That assumes one source, because in fact, of course, the total exposure from all sources at a designated point mustn't exceed the design dose constraint. So life would be easy if we had narrow beam transmission, because with narrow beam transmission, we've got the Beer-Lambert law, and it's just an exponential attenuation. So using a linear attenuation coefficient mu, but of course we can't do that because X-rays aren't monoenergetic and narrow beam considerations just do not apply. We have a broad beam geometry. So measurements and simulations of transmission of X-rays through lead, concrete, and a variety of other materials give us curves that look like this. So more attenuation to start with than linear attenuation. Notice this is a log scale. I've shown you here lead and concrete. So this is what it always looks like. And 40 years ago, Ben Archer and his team identified that you could fit empirically derived constants to transmission and come up with two equations relating transmission and thickness, or thickness and transmission, using alpha, beta, and gamma, which are empirically derived. And we have these for lead, concrete, steel, gypsum wallboard, plate glass, wood, barium, plaster, and brick, which is just about anything that you're going to use to shield X-rays for a variety, or a range rather, of KDs. And because they're empirical, alpha, beta, and gamma actually take leakage into account because they're measured, which means that's another reason for just ignoring leakage altogether. They're different for primary and scattered radiation, but in practice only below 100 kV, and they're tabulated in the book that we're talking about. So that's what we've got. We know what we're trying to do. We're trying to attenuate. We've got an equation for attenuating, and we know that X-rays intensity falls off with square root of with distance squared, sorry. So just a quick mention of the shielding problem for primary radiation. Primary radiation radiography, chest, shoots through hips, erect spines, etc. And here it is in a nutshell. We have air kerma here, D1, D2, the kerma here, presently the attenuation by the barrier and possibly the Berkey. We assume that the patient has no attenuation. This is in case the beam isn't totally collimated by the patient. So it's, in principle, it's very simple. In practice, there are a few things that one has to think about, but that's really it in terms of primary radiation. What about scatter? Scatter's everywhere, and it's much more complicated to predict than primary radiation. It's ruled by the Compton effect, Klein-Scheiner equation, pretty insoluble in terms of anything analytical. So we resulted to making measurements and doing Monte Carlo simulations. This just shows what we did. Rando phantom, which I think many people will be familiar with. we did this at energies between 50 and 125 kV. Ion chamber 30 to 150, where 150 is going back towards the tube, 30 is going forwards. And we measured the scattered fraction expressed as micrograde per cap. And for those who don't know, cap is Kerma error product and is the product of the Kerma and field size and is independent of distance from the X-ray set. So when we did these measurements, this is the typical curve that we got. Same time S-shaped curve for all KVs, 50, 70, 85, 100, 125, with more radiation going back towards the tube than going forwards. This is good because this is what people know to be the case. We were able to model scatter factor here in terms of angle theta and came up with this rather awful equation. We also looked at scattered spectrum from our Monte Carlo simulations and identified that there is more X-rays going backwards towards the tube, but of course they have a lower quality, as you can see from this. And this just shows you how the quality, i.e. the penetrating ability of the X-rays, varies with angle. So, we're able to show that more scatter back towards the tube, increasing half value there towards the patient. That makes it all a bit difficult. But if you think a bit more, and if we have an X-ray beam incident on a patient parallel to a wall here, and we find that we've got most X-rays going back towards the patient, most X-rays back towards the tube rather, fewer X-rays or lower fluence towards the patient. If we account for the fact that there is an inverse square law, we actually can see that there's a point at which there's going to be a maximum. And that point is about 120 degrees, it's 117. Which means that we can feed 117 degrees into our equation here. And come up with a much more easy equation that the maximum scatter is 0.031 times the kV plus 2.5 per gray centimetre square, which is the unit of cap at 1 metre. And if we then make the assumption, which is going a bit, that 85 kV represents a reasonable but conservative value for kV, which it probably does, we could actually simplify it right down to S max equals 5.1 micrograde per gray centimetre squared. And what's more, empirical measurements allowed us to be confident that the inverse square law is a reasonable approximation for the reduction in scatter with distance once we have these equations. So we've got simple equations relating scatter with the Kerma area product involved in the exam. What about interventional cardiology labs where we actually introduce additional copper? Well, we did similar things and identified that for interventional cardiology, the number becomes 8 micrograys. So we have simple numbers. So I say, you know, using science to generate an art almost. Okay. So that's where we are. We can relate scatter, and once we have the scatter, we can use the same idea, the barrier, the same equations to predict the transmission required to get our radiation doses down to the desired dose constraint. What about CT? Well, scatter factors are linked to dose length product and have the form scatter equals Ks divided by DLP. And Colin is going to go into this in much more depth in about a minute. Exposure to tertiary scatter from concrete slabs. I mentioned this already. Colin's going to discuss. There's also a reference here. But in high workload, i.e. lots of radiation fluence hanging around, like fluoroscopy or CT, you can get scatter that's reflected from the walls, tertiary scatter. And Colin's going to explain how we approach that. Okay, so to summarize what I've been saying, shielding is about minimization of risk and compliance with legislation. The dose limits are based on effective dose, but they're a risk metric, effectively part of the dark arts, and they're not for shielding calculation or assessment, our aim has been to come up with a way of designing shielding that is a LARP, that uses precisely defined dose quantities that are used in radiology, i.e. KERMA, and then to come up with an evidence base for the factors and methodologies that we've done. So that's me, I think, gone through the principles involved in a very, I have to say, quite rapidly. So thank you for your attention, and I'll stop and hand over to Colin.
I'm going to talk about, as David says, the applying a similar methodology to the assessment of scatter from CT and evaluating the shielding. So say something about the initial considerations, the dose rates from scatter, and in order to get scatter, we need something similar to KERMA area product in radiography and fluoroscopy. And so the obvious one is the dose length product, which measures all the radiation going into the patient. So I'll give example shielding calculations, talk about the protection of the ceiling and the floor, look at tertiary scatter around and over barriers, and then say something about what happens if the workload increases. So a simple scanning room is unlikely to be adequate. Insufficient space around the scanner, doors too small to allow easy access to trolleys. There's not enough space in the control cubicle because you might have lots of other staff needing to be there. The staff unable to enter a protected area, and you also get quite a level of scatter from a wall, which will require a shielded door to protect the staff. So the general arrangement for CT rooms is something like this, with the CT room and control area and surroundings, so quite a large control area. And so here we've got a much wider entrance for the trolley access. The cubicle window gives us a good view because you need to look at both the patient and anyone who might enter the room. And the control cubicle gives space for several staff in the cubicle, and there are protected doors into both the room and the control cubicle. So it's we want to use the dose length product, and so what we wanted to derive was coefficients providing a link between the air KERMA and the dose length product. And so the scatter factors of this form, where we've got the air KERMA divided by the dose length product of what we were looking for. So we wanted really values at 1 meter from the isocenter. Now, in the past, people had done measurements on grids and made sort of contour plots, but really, as we wanted the values at 1 meter, it was more logical just to do measurements all the way around the gantry at 1 meter. And if the inverse square law could be applied, then that would allow us to derive a full contour plot just from these sets of measurements. And we found that really the inverse square law was a reasonable approximation for the decline in scatter from CT beyond about 0.6 meters from the isocenter, which suited us. So we did measurements all the way around at 1 meter, apart from behind the gantry, where we had to get 1.5 meters. But that gave us a complete set of measurements all the way around that we could then convert to 1 meter. And you notice here that the isocenter is closer to the front, and this seems to be followed in all of the different models that we looked at. So this is the sort of plot we got. So this is the angle around the scanner in the horizontal plane. This bite out of the scatter here is caused by the gantry. And these are scatter dose levels per DLP measured from scans of an anatomical phantom. So the pattern, these dots, different colours, show different scanners, and so we looked at all the main manufacturers, Philips, Toshiba, Siemens, GE, and also we looked at 140 kV, just a few dots at 140 kV here and here, but there didn't seem to be all that much difference between 140 kV and 120 kV as far as the scatter pattern was concerned. And we did similar measurements linked to the head scan DLP, because the head scan DLP measured on a different phantom, the actual value of linked to the amount of radiation is less than half of that for the body. So we needed to have the same type of data for head scans. And we also did plots in the vertical direction, and there was little difference between the ones in the horizontal and vertical directions. So once we got those sets of data at 1 meter from the isocenter, we could very readily generate contour plots of this type. So this shows the sort of hourglass arrangement, where you get lots of scatter here, but you get quite good protection from the gantry here and here. And these are well defined and reproducible because the tube follows the same path every time around the patient. And these are other examples of a body scan from a Philips scanner and a head scan from a GE scanner. So we wanted to replicate those sort of patterns. So we wanted factors that we could generate something quite readily. So really, we looked at between 20 and 40 degrees. This is from the isocenter, remember. So we wanted factors for this region and factors for the region behind the gantry. So the scatter at the head region for the body phantom was about 0.3, and at the front of the scanner about 0.36, though one could use the same value for both. As far as the protection from the gantry is concerned, it's about a factor of 10, and behind the gantry we reckon that a reasonable value was 0.04 microgray per milligray centimeters. So all these are at this point with a ratio of 3:2 closer to the front of the scanner gantry. So we've got these factors then, and we need to well, yes, so these are the factors for the body scans, and these are the factors for the head scans. So you can see that the head ones are just a bit less than half of those for the body. But again, the protection behind the gantry is by a factor of 10. And these are the angles over which we would apply those to produce this sort of hourglass scatter arrangement. And so that shows a couple more comparisons for different scanners. But what we want is the amount of scatter that we're going to get over a year. So we need to be able to calculate workloads. So we looked at annual workloads for 38 scanners, and these were the values that we got. So these were the mean values, the third quartile, and the maximum for body scans, head scans, and total. So we need to treat these two things separately. So to calculate the amount of scatter, we use an equation like this. So this is the number of scans per week multiplied by the number of weeks, multiplied by the DLP, and then multiplied by the scatter factor. So this is for the body and this is for the head. So we do the two calculations separately and add them, and then we'll use the inverse square law to calculate what the value is at a particular wall. So we've got the scatter air kerma from the DLP and the distance to the wall. We've got the dose criterion that Dave talked about, dose constraint divided by the occupancy. So the transmission we need is the dose criterion divided by the scatter air kerma. So here's an example. We've got body scans, say 4 times 10 to the 6 milligray centimeters, head scans. So those are annual workloads that I'm going to use for the example. The wall closest to the isocenter is this one at 2 meters. When we want to consider protection of the door, because of the protection of the gantry, we apply an angle of 30 degrees and then can calculate the scatter at that sort of distance. So distance used for shielding calculations is that at 30 degrees beyond the edge of the area for which the gantry affords protection. So here we've got our workloads, our KV, we've got the distances, we've got the occupancy, which was assume 100% here, and the dose constraint. So we've got our scatter factors for the head and body. And we can then calculate the dose at door B. So that is the body part and the head part, and divided by the distance squared for the inverse square law. So that's the dose at the door. A similar calculation for the dose at wall A. Here the distance was 2 meters, so convecting for the inverse square law. So that's the dose there. And so we can calculate our transmissions from our dose constraint divided by these dose values. So those are the 2 transmissions that we need for the wall A and the door. So using the equations that Dave showed you, we have coefficients here for lead for 120 and 140 kV, and the values for 120 kV for the transmission we want are 2.2 millimeters of lead for the wall and 1.8 millimeters for the door. So this shows the form of the curve of transmission against thickness that Dave showed earlier. So we don't often use the shielding factors behind the gantry, but the shielding provided is quite useful because we can put, say, high ventilation ducts in the area protected by the gantry. And if we weren't able to do that, then we'd need to include some sort of baffle, such as I've shown here too, so there weren't scatter X-rays going directly through the penetration. So what about the floors above and below? Again, we can take the gantry into account. So again, we can look at angles of 30 degrees. So we consider X-rays that are incident at an angle of 30 degrees. So we calculate results for someone at 0.5 meters above on the next level above, or either 1 or 1.2 meters above the floor on the level below. Protection afforded by the gantry means that only angles of incidence more than 30 degrees need be considered, and we did consider whether tilting of the gantry needed to be taken into account, but for measurements others have done, this really had little impact. So if the vertical distance is d, then the distance from the isocenter for calculation is d over cos theta. So for oblique incidence, we use an equivalent barrier thickness equal to the mean of the actual thickness and that in the direction of scatter, because that's the direct transmission, but you can get scatter at other sort of angles. So if the calculated thickness is x, then the thickness of barrier that we required is given by this equation here. So we're averaging the different thicknesses if you look through different directions. So here's a shielding calculation for here we've got the distance corrected by the cos theta angle we've got the same occupancy and dose constraint. We've got the same scatter factors. We can calculate the dose of the body and the head, and then correct for the inverse square law to get the dose. And that gives us a transmission of the ceiling slab of 0.003 in the same way as we got it for the walls. And using a similar equation, but this time, because we're dealing with concrete, we have different factors, and then we can calculate a barrier thickness, taking account of the sort of angulation and the sort of averaging that I talked about before. So this ends up being 124 millimeters of concrete. Those factors are for high density concrete though, and sometimes the density of the concrete might be less, so we need to make adjustments for density. The concrete slab might have been sort of poured onto some sort of decking, so there might be differences in thickness. Even if the ceiling looks solid, a sort of hollow core is often used to give more strength for a sort of lighter arrangement. So you need to have some information about the ceiling composition, the ceiling thickness. So that's really all I want to say about the ceiling and the secondary scatter. But as Dave mentions, there's also tertiary scatter. So how large are these dose levels? So do you need a door on the control cubicle? How tall should the screen be? So we did quite a lot of measurements and also calculations to simulate the how the scatter changes as you move a distance behind the barrier. So this shows some of our measurements compared with some of our calculations. So all this was really done to derive some equations that we could make reasonable assessments of the scatter. So these were the equations we came up with. So they're very approximate, but they will give some information. And so this equation for the relates to ones where the distance d is 3 meters, and this equation where it's more than 3 meters. But the biggest factor is the distance of the isocenter from the scattering wall. So that's taken into account in this exponential component. So those are equations you can use. But tertiary scatter from the sidewall, the values actually are quite large. So if this is the distance from the wall, and you can see it as it decreases, the 2.5 meters level gets up to 8 milligray. So a door will almost always be required, and it should be specified to protect against secondary scatter from the patient, so that if you have a door, then people standing behind it will be protected. But then there's also the ceiling. The scattering of X-rays from the ceiling over short barriers is high enough to give staff a radiation dose. So they've got this big gap here where you get scattered radiation through. And so we again did measurements and did sort of calculations looking at scattering from different elements across the ceiling. And we came up with these curves. So we've got scatter air coma per DLP against the height of the barrier, and these are the different heights of ceiling. So if you've got a high ceiling, a long way away, so we don't get too high a scatter level. But if we've got a low ceiling, 3 meters, then we get quite a lot of scatter, because there's the scattering surface is quite close to us. So these equations are more complicated. So what we did was fit lines to these graphs to try and generate simple equations that could be used for predicting tertiary scatter levels. And this is the equation we came up with, again incorporating the DLP for the body and the head. So B is the height of the barrier, and C and M, they're constants. So they're given in our book. They're also given in a paper that we've written on this. The ceiling scatter for 5,000 gray centimeter workload and a 2 meter high barrier would be, depending on ceiling height, between 2 and 4 milligray. So it's not insignificant and needs to be thought about. So another thing, what happens if the workload doubles because you use there's more demand, more patients, but this transmission is on a log scale. So if you went from 0.01 to 0.005 somewhere, it's a much smaller increase on top of the shielding that's present. So if we half the transmission, these are the lead thicknesses that we require. So it goes up from 1 millimeter to 1.3 for the door, 2.2 to 2.5 for wall C, 1.9 to 2.2 for the control window. So it's just adding a little bit more will take account of higher workloads. So if we look at plots of lead thickness against DLP, for a barrier at 3 meters from the isocenter, 1.9 millimeters sufficient for the lowest CT workload. If the workload is doubled, we need 2.2 millimeters. If it's tripled, we need 2.4 millimeters. So that's something to take into account if you think the workload may increase in the future, or if you have getting a new scanner or something in and the workload is going to be increased. It doesn't necessarily mean that you will have to reshield the wall or increase the shielding in the wall. So in summary, calculation of shielding is based on the DLP workload for CT. You need separate scatter factors for the body and the head. Attenuation afforded by the gantry can be taken into account. We don't use that value as much, but we more use the gantry shielding to limit the distance limit the distance on a wall that we might need to use in a shielding calculation. Likely DLP workloads are between 3,000 and 8,000 gray centimeters. The obliquity of the scatter on the ceiling can be taken into account, both in terms of the distance to the ceiling and also the obliquity of the scatter going through the concrete block. A dorsal control cubicle will almost always be needed for CT. Tertiary scatter from the ceiling slabs can be calculated. Wall protection may be required to the level of the ceiling slab. And CT rooms may require 2 millimeters of lead or more, while often fluoroscopy and radiography needs may be less than 1 millimeter. So the sort of standard code 3 is suitable in most cases. So I acknowledge the other members of the shielding working party and give another plug for our book, which is now available free as an e-version from the BIR website. And also give you these other 2 references. All the CT data and more is given in a paper that we published in the Journal of Radiological Protection. And similarly, the data and the measurements from tertiary scatter are given in a paper, so both published in the Journal of Radiological Protection in 2012. And that's me finished. So I'll thank you for your attention, and we await any questions.